Hello class, this is a little help session for the lab number 9, which is on atmospheric moisture and severe weather. So I'm just going to run through what I think you need. Otherwise, I'm going to skip through some of the questions and let you try to figure them out on your own. Okay, so this should be your lab handout as you go into Blackboard and go ahead and find it. So I'm not going to go through the lab objectives here. You're free to read them on your own though. Materials that you'll need. So you will need red and blue colored pencils. You'll need a printer. I did not outline that here, but you'll need a printer and the red and blue colored pencils. You will need access to Google Earth. The installation is super short and easy, and I believe that if you're using Google Chrome, it can launch without downloading it itself. However, if you don't want to do either of those things, use Google Chrome or access Google Earth, there is a secondary document that you can find also on Blackboard that has the necessary images to complete the part where you would need Google Earth. So you don't necessarily need it, but it is very useful to complete the lab. And then you also need a scanner or have the ability to take a very good photo of whatever you print and then color. So there is an alternative. If you don't want to print and color the map, you can also use PowerPoint or some other sort of tool. I use PowerPoint because I already know how to do the things that it needs to do, but you're free to use whatever other source to complete it. So I'll show you how that would work if you don't want to go ahead and print it and color it, although that is the easiest thing to do, I think. Okay, so the first part of your lab. So the 3 phases of water and relative humidity. So I'm going to go ahead and read and stop every now and then if I need to. So water is more abundant on Earth than on any other planet in our solar system, and is the most abundant compound on Earth's surface. Water regularly exists on Earth in all 3 of its physical states. Those are solid, liquid, and gas. The changes between these phases require an exchange of heat energy. Heat is always either absorbed or released. The phase changes are evaporation, condensation, freezing, melting, sublimation, and deposition. So all of those are the changes from one of those phases to the other. Droplets on the outside of a glass of ice water, come from the air, not from the water inside the glass. This means that there is water in the air all of the time, but not as a gas, so we can't see it. But as a gas, so we cannot see it. This water is referred to as water vapor. So here's the first question, and I'm not gonna merit much of an answer here from me. So water vapor in the air is kept in a gaseous state by heat energy exceeding a threshold. The solar energy that warms the Earth also supplies the heat energy to keep water vapor in the form of a gas. So when do you think would be a time of day, or what times of the year is there less heat energy available from the sun? So basically, when would be the coldest times, based solely on solar input. Second question. When there is less heat energy available, less water can be kept in the air as a gas. Some of this water vapor goes through a phase change and becomes liquid or solid water. So what kinds of liquid and solid water do we see as a result of this process? So basically, when the water changes from being a gas to becoming liquid or solid, how does it express itself here on Earth? Third question. Humidity describes the amount of water vapor in the air, but humidity is not constant. Water vapor is more abundant where there is a large amount of heat energy and a large amount of liquid or solid water to be evaporated or transpired from vegetation. So describe the 3 places on Earth, where this combination occurs. So basically places where you would have a lot of water vapor, right, and where you have a fairly large amount of heat energy or input from solar energy. Okay? So I'll let you think about those. All of these on the quiz online, there are options for all of them. So hopefully after you have thought of some of those options, the questions online won't seem completely random. Okay, so now comes the trickier part of part 1. So relative humidity describes the amount of water vapor that is in the air relative to how much the air can hold. This depends on the temperature, as hot air has more heat energy available than cold air to keep the water vapor in a gaseous phase. When the air is holding the most water it can, as a gas, it reaches saturation. So the temperature at which saturation occurs is called the dew point. Okay, so dew point is when you reach saturation, which in itself means that the air can no longer hold the water as a gas. So the gas, there's just too much of it, there's too many particles, and so then it will turn into either liquid or solid water, no longer gas. That's when you reach saturation, and that is what we call the dew point. Okay? So, again, just to tie those things together, when the relative humidity is at 100%, that is going to be saturation or dew point. So we use a psychrometer to measure relative humidity. A psychrometer has two thermometers, one which stays dry and measures the air temperature, and one which is saturated to measure the wet temperature. So here's going to be the example that we're going to use for the first question. So as an example, on an April day in Boise, there is a little bit of moisture in the air from a weak storm that passed through the area. The amount of water vapor in the air is 5.2 grams per meter cubed. So that is the amount of water vapor in the air at the moment that is measured. So here I'm going to give you this equation. This equation is going to be pretty key to complete the table below and complete some of the questions below. So the equation says relative humidity, which is going to be some percentage, is equal to the actual water vapor in the air, so whatever you measure the water vapor in the air to be, divided by the maximum water vapor capacity in the air at a current temperature. So this value down here is a set value. So say that if the temperature is 0 degrees Celsius, the maximum water vapor capacity that the air can hold at that temperature is always 4.8 grams per meter cubed. So there's always a set value for this bottom part depending on the temperature that you're experiencing. This actual water vapor in the air value does change depending on what you're measuring. And then whatever that division that you get, that you're going to multiply that times 100 in order to get the relative humidity, so to make it a percentage. Okay? Okay, so using this scenario, the one that we just said, that example, and the equation above, calculate the relative humidity for each temperature of the table below. So, again, the actual water vapor for that example is 5.2. You know that the value for the maximum water vapor capacity for each of those temperatures. So you just have to go ahead and plug and chug, and you get the answer. So for example, in the first slot there, you would say, okay, so I have 5.2 as my actual water vapor divided by, so let me go ahead and show you that actually. 1 second. All right, so this is that same formula. So we're going to go ahead and try the first couple of rows within that table. So the first row should be 5.2 being the actual water vapor that there is measured at that time. And then that is divided by, I believe it's 3.3, but we can check on the table. Yep, so 3.3 at the -5 degree temperature. So go back here. So that's, oh, sorry about that. 3.3, and that you multiply times 100. So the value that we end up getting here is 157%. And that's going to be a percentage because it's relative humidity. So it's incredibly humid. So because the humidity is greater than 100%, that means that it's fully saturated, and that means that it's probably raining or snowing or hailing or some sort of precipitation is taking place. okay? So if we do the next value over, so the one for the 0 degrees Celsius, we say, okay, the actual water vapor in the air that was measured, it's still 5.2. And now my value here below, based on the table, is 4.8. So we input that, and we get 108% relative humidity. So you basically input those back on the table, and you do it for all of those different values. Great. And so what that means is that at 6 and 7 a.m., again, the relative humidity is greater than 100%, so it's going to be precipitating in some way or another. As you'll see, as you get further within the day, the relative humidity is going to change. So that's going to determine what you end up getting for this table. And the questions online, I think I ask you one or two of these different temperatures, so you tell me the relative humidity at those temperatures or the time of day. I can't remember exactly what it is, but you can just match based on the row that you're looking at. Okay, excellent. So that's how you fill in number 4. So let's go on to number 5. So what does relative humidity above 100% indicate? So again, if it's 100%, what do you think that means based on what we have talked about previously? I'll let you go ahead and think about that. Okay. Using the chart below, graph the change in temperature over time in red and the change in relative humidity over time in blue. So if the relative humidity is over 100%, the graph, just graph it as 100%. So the first graph the data points and then connect them with a smooth line. You should end up with a red line showing change in temperature over time and a blue line showing change in relative humidity over time. So I'm going to go ahead and show you what I did for those first 2 measurements that we just input into the table. Alright, so I'm going to go ahead and I'm using PowerPoint here just so you know. You're free to do so. So you just go insert shape, and I think it's, what is this? Okay, so we're going to go ahead and start. So at 6 a.m., the temperature was -5. So temperature, again, here is this y-axis on the right. So we're going to mark that point. At 7 a.m., the table had said that the temperature was at 0 degrees Celsius. So we'll mark that point. At 8 a.m., it was 5. At 9 a.m., it was 10. So conveniently, the temperatures of these tables are all linear. Of course, that's not how most places work, but for you guys, it was fairly straightforward here, so we'll continue to mark those points and hence connect them with this line that I'm making. And as per instructions, this was supposed to be a red line. Oh, sorry, wrong format. So shape, red, we can make it a little thicker. Okay. So that is the line for the temperature. Now you're going to fill in the line for the relative humidities that you calculated. So because we only have calculated 2 so far, which again were, sorry, this deleted itself, 157% for the 6 a.m. one and 108% for the 7 a.m. one, I'm going to mark those at 100%, right? Because the table doesn't give me any higher values. So we'll do the same thing. In my case, we'll insert a curve at 100% for both 6 and 7 a.m. So once you have more values, you'll see how these change throughout the table. But for now, because that's what I have for you as an example, that's what we'll put. So again, you can use these programs if you want. It's easier if you print it and just fill it out on your own. But you're free to use these. You will have to submit, I don't think this graph, but another one, to the lab quiz online. Okay? Alright, so again, once you have filled that out, the next question is, describe the relationship between temperature and relative humidity. In other words, what did those values that you input onto the table look like? Maybe there is no relationship at all that is easy to see, but maybe as the temperatures rises, relative humidity also rises, or maybe there's a weird sinuous pattern to it, maybe it decreases, I don't know. So after you figure that out based on your values that you calculated, go ahead and tell me what the relationship is.